Okay, so welcome to today's course. Sorry, lecture. This is our syllabus as we usually look at it quickly. So we'd be doing random forests. I know we did these techniques. We went over the metrics in last call on how you would evaluate any technique. So even for random forests, the evaluation would be the same. Different metrics involved. So let's jump into random forest. It's a very, very popular technique. Actually, in AWS as well, I've used random forest on a large scale quite a few times. So um, I'm saying that just to back it up even more. Okay, so okay, there we go. So basically, just like I've said, SVM falls under what is known as a set of methods called kernel methods. You've seen SVM. Similarly, deep learning and neural networks are all in one sort of a family of methods that are similar in some sense. Random forest is more like a decision tree method. So you're essentially building a tree, and as you go to the bottom of the tree, you're going to be making some sort of a final classification at the leaf of the tree. At the root of the tree, when you start, you take all the variables into consideration. And at different nodes, you take different decisions based on different variables. And once you reach the leaf, you have the final class label. So it's a decision tree method. Another bucket it falls under is what is known as an ensemble method. So just to give a overview in the first 2-3 slides, I just want to tell you what an ensemble method usually is. This is a high-level slide. We would get into very specifics of how the random forest works after the starting 3-4 slides. So at high level, ensemble methods are, ensemble means basically mixing things. So basically, we're not learning one classifier, we're learning many classifiers, and we're trying to find a way to combine the result of multiple classifiers. So you have multiple experts making different decisions. So maybe if it's an email classification example, the spam, no spam, right? Some classifiers might be SVM, some related, some may be deep learning related, some may be random forest, some may be something else. And then you have different classifiers thinking whether a particular email is spam or not, and then you want to take a majority decision of some sort, right? Some simple majority decision would be just to count. If you have 5 classifiers you're using, then your final ensemble decision could be the majority thinks it's spam or no spam, for example. Or you could do some sort of a weighted decision where some classifiers you have more belief in, so they may give you a bigger weight, and the other may give a smaller weight, some sort of weighted average. Now, there are different ways of combining, but this idea of combining multiple machine learning methods into a final output, the output of multiple into one final output is known as an ensemble method. So the overall idea is, on average, instead of sticking to one single classifier, maybe a group of experts or multiple classifiers might hopefully do better than just a single classifier. That's the overall high-level idea in an ensemble method. So that's what he's writing here, right? So if you have a classifier H, that is a function that goes from your data X to your label Y, which is either -1 or 1. That H could be instead a function of multiple classifiers. There are different 2 classifiers here, right? That kind of thing. Okay, so another concept that random forest uses is known as bagging. This is very important in some sense. So we talked about how we combine. By the way, the forest is a kind of a funny notation, because what random forest does in terms of ensembling is the following. It builds multiple decision trees. So you have multiple trees that try to classify, and then it tries to combine the result of multiple trees. That's why it's ensembling in random forest as well. And for the funny reason that you're having a bunch of trees, it is known as a forest. So it's a random forest. Another concept that random forest uses is known as bagging. This is kind of a very interesting concept. Um, so basically, all it does is very simple to explain. So when you're trying to estimate something, what bagging does is you take your input data set and then you sample a smaller subset from your data set. But the sampling you do, there are two kinds of samplings you could do. One is in general sampling with replacement or sampling without replacement. Say if you had a bucket of red and blue balls, sampling without replacement is as follows. If I want a sample of 10 balls, I randomly put my hand inside and I randomly pick a ball and then I put it outside. So I'll see what that ball is. It could be a red ball. Then I put my hand in again, I take the second ball out, put it outside the bucket, put my hand in, take the third ball out, put the ball outside. So the main thing I'm pointing out is I'm taking the ball, once I'm taking it out, I'm putting it aside from the population. So the next time I sample, that particular ball is not there, right? So this is known as sampling without replacement. Sampling with replacement is I take a ball out, I see what color it is, note it down, and then I put the ball back into the bucket. So that is known as sampling with replacement. Is follows. Sampling with replacement is very useful in some sense. The reason is what I want to give you here. So say your data set has a distribution. The red ball, blue ball thing has a distribution as follows, for example. So this is the number of red balls in the bucket in reality, and say this is the number of blue balls. Okay. If I do sampling with replacement, if I say the bucket has 10K balls, 10,000 balls. Okay, it's a very huge bucket. And say my sample, I need a sample of 1K balls, 1,000 balls, right? Now, if I do a sampling with replacement, which is basically, like I said, right, a lot of balls in here. I basically if I want a sampling with replacement of a set of a size of 1,000 balls, what I do is I take one ball out, I put it aside here. And then I take the second ball out, I put it aside here. So I collect 1,000 balls here. Okay. Once I have my set of 1,000 balls, so I have my subsample I have generated from this total sample. Now if I draw a histogram of this again, if I count how many red and blue balls I'll have, I will bet you the shape will look very, very similar to this. So basically what sampling with replacement is doing is it is trying to preserve the distribution that you originally have in the population you're sampling from. So the distribution in the original population looks similar to the subsample population. So now what bootstrapping does is going one step ahead. If you want to compute, say, some statistics or some answers out of your original population, right? Say in this situation, one thing you want to know is maybe what is the proportion of red balls, right? And what is the proportion of blue balls, right? You want to know, is it 70%, 30%, or is it, is it 0.7, 0.3 proportion, or is it 0.5, 0.5, which it doesn't look like in reality, or maybe, but you don't know the reality. All you have is the bucket, right? You don't want to take all the 10,000 samples and then compute the proportion of red and blue. You want to ideally come to the true answer from looking at just 1,000 samples, and you want to hope the proportions of red and ball you estimate from this subsample is as close as possible to the true proportion size in this sample, right? This is the population answer, this is the sample answer, but you want this answer to be as close as possible to this. So what bootstrapping does is what it does is instead of computing proportion on all the 10K balls, you take a subsample with replacement. Sorry, what I showed you here was without replacement. Now what with replacement does is it takes a ball, it puts it back again, and then you just note down what you took. That is the without replacement. Sorry, I might have confused you. I first showed you with replacement, but bootstrapping is all about, sorry, I showed you without replacement, but bootstrapping is all about with replacement. Okay, bootstrapping is with replacement. So yeah, there you go. My bad. So what bootstrapping does is to answer this question of how many proportion of red and blue, it takes a subsample, smaller sample with replacement. And then what it does is whatever you want to compute, it computes on this subsample. So I will compute how many proportion of red and blue. Maybe I get an answer 0.71 and I don't know, right? 29 in my first sample. Okay, then what I do, I put this whole bucket inside, all these 1,000 balls back into the bucket. So again, I start from where I originally was. So again, I'm back to the original bucket. Now again, I take another subsample of 1,000 samples, again with replacement. So I take it, I put it back, but I note down what I took. So, okay, I got one red, I put it back. Then I take, I got again red, again I put back. I got, third time I got red. Now I got blue once, now again red, now 2 times blue. Whatever. I write down everything. So this is what I wrote out in my second sample with replacement. I again compute the proportions because that is what I want to answer with respect to 100K balls. Right? Then maybe I get some answer again. Maybe this time I got 0.6 and 0.4. Okay. Then I repeat this process. Now, this whole process of taking subsample with replacement, computing whatever I wanted on the subsample instead of the whole sample, then putting that back and then doing that again. If I do that, say many times, say, I don't know, K times, so maybe I could have done it 5,000 times, I could have done it 100 times. And then I take the average results. So these are the results from the first set, these are the results from the second set in terms of proportions. I average all these results. Then the result I get is known as bootstrap, is the result of what is known as bootstrapping or bagging. And by the way, bagging, the full form of it is known as bootstrap aggregation. So bootstrap aggregation. Bootstrap is referring to sampling with replacement. The sample is known as a bootstrap sample. These are different terminologies, but all it is sampling a sample with replacement, a subsample with replacement. Aggregation is nothing but how you aggregate your results, and here the aggregation is just an average. So what this formula is showing is, if X is your data set, capital B is the number of smaller subsamples you're taking, bootstrap subsamples. So each time you're computing whatever you want, which is known as FB of X on the smaller subsample, then you're averaging all your B results. So basically, that is known as bootstrap. So I'm computing the proportions on this subsample. I'm doing it many times, K times, and then I'm averaging it K times. In his formula, K was known as B, so you can call it B if you want. So you're doing it B times and it's averaging it. Okay. So that average result this way of estimating your answer that you want to estimate, which is in this case the proportion, right, of red and blue balls, is known as the process of bootstrap aggregation or bagging. And the theory is this kind of an average goes close to the true answer as quickly as possible and as accurately as possible. So it's a great way to estimate the true answer. Okay. And also, the reason for putting your ball back, so why are we doing sampling with replacement, is because you don't want to disturb the original distribution of your data set. Your original distribution is looking like this, right? This, I told you beforehand, but you won't know this because unless you really count all the 100,000 balls, all the 10,000 balls. But there's a true answer. So when you take something out and put it back, you're not disturbing the original distribution. Okay. So each time from the original distribution, you're computing something, you're averaging it, and that will converts to the true answer. Basically, this is the known process of bootstrap aggregation. There's a lot of theorems that say why this converges. And this guy called Brayman, he passed away recently. He was a professor in statistics at UC Berkeley. This guy introduced the random forest algorithm, so that's the reason we are taking his name here. Okay, back to the slide. This is another concept that random forest uses in its workings.
One sec.
Sure.
Here.
Sure.
So what you did is in your diagram first without putting back, and second one is keeping back. So that is what the chart, right?
Yes.
Okay, got it. So that is giving so without replacing, with replacing means like what exactly it gives kind of a hypothesis. What kind of hypothesis? Is it repeatable or on what basis you choose that option?
Yes. Okay. Yeah. So this is a good question. This is like an extension of the original question, right? So I showed you two processes, with and without, and then the question we can say in what situation without is useful, what situation with is useful, that kind of thing. Okay. So um, the bootstrap aggregation, like I said, is with replacement. If you want to compute some statistic, right? Here I gave an example of proportion of balls, but it is very extendable. It's not just that, because from a different data set, you have different questions and hypotheses you are trying to answer. In some situation, you might be trying to answer literally whether your set of out of your set of 10,000 emails, you want to answer the classification problem, right? Say the cartoon example, like which email is spam and which email is not spam. Now, your way of computing now is not as easy as counting the balls, right? Because of classifying is not as easy as counting the balls, because here your B things that you're trying to do previously were like literally you were counting balls manually or whatever. But since you're talking of classification problem, in Bootstrap aggregation, what you want to do is, what it suggests, the idea it suggests and guarantees is, if you have individual classifiers of different kinds, so you can have, say, one random forest class, say you had 3 of them, or B of them, right? You say one is some random forest classifier, some SVMs that you have trained on your data, some that you can train, some neural network, some other thing that you learned later. Then the idea is you don't have to apply the classifier on the entire 10K data set. Or your original data set of emails could be, I don't know, 100K or 1 million, whatever. You don't have to apply it in all. You only can apply, you can just, what this guarantees is, you can apply your SVM on a smaller data set. Obviously, the size of your bag, the smaller data set is known as a bag. So, or your smaller subsample need not, again, if it is too small, if you take a 100,000 email data set and if you apply your random forest on 5 emails, then it's not good enough. But if it is reasonably small, so maybe from your 100,000 you take a subsample of 10K emails, 10,000, and then you apply random forests on subsamples of 10K emails. But then you can also apply SVMs and different classifiers. And then the question is, how do I aggregate the decisions that it is all these classifiers are making on smaller subsamples, so that the aggregated decision still holds good on the entire 100K samples, entire original samples. So there, what bootstrapping suggests is again the same thing. All it suggests is take a resample, compute your individual answers, and just combine them simply by proper average, just by adding it up and dividing by how many times you did it, how many samples, how many bags you collected, how many subsamples. So Bootstrap aggregation is useful for estimating some answer on your bigger population using multiple smaller populations. And it guarantees that this average goes to the true answer on the bigger population pretty accurately. If you have enough number of bags and if your size of bag is good enough, or bag refers to the subsample. This is where resampling is used. Resampling means with replacement, which is bootstrapping, which is what we're talking here till now. This is what is used in random forest. Now the question is, when do we sample without replacement? Without replacement is good enough if you want only one sample, for example, where you don't have to literally estimate anything. You just want a sample, a smaller subsample whose distribution is kind of similar to the original distribution, right? So then you just uniformly pick. And since these are more common and these are less common balls, obviously some sort of a similar behavior you'll observe in your smaller sample of 1K that you picked without replacement, just randomly picking. But then there is, if you want to compute a statistic from a smaller subsample and you want to, from this smaller subsample, and you want to make sure it gets as close as possible to the bigger subsample, and if you have multiple ways of computing the statistics, then a good way of combining it is not, if you want a good way of combining it, then with replacement will give you a better answer than without replacement. If I did the same process, but if I did it with replacement in the same proportion estimation thing, then my bootstrap aggregated sample will be closer to the true answer. Say the true answer was something, say it was 0.68 and 0.32 or something. for red proportion, blue portion, then my bootstrap sample is guaranteed to get closer to this faster and more accurately than the without replacement sample. That is the only difference if you're combining multiple answers. So say it is like a poll, for example. Say you had 100 people trying to guess if Democrats would win or Republican would win in the future, in the next election, whatever. And if you did a sample with replacement, which is like this. So basically in each bag, each subsample, sometimes some intersection might happen, right? Because maybe 5 people might have answered here, they might have ended up here as well. But the rest of the 995 people might have been different because since you're replacing, some things might come back again. If you take that kind of a subsample and if you take poles, if you take these bags B times and if you take B different poles and you average those poles in this way, this will guarantee to give you closer answer to the true answer than doing it individually. So that is the bootstrapping. So if you search for yeah, so there is, I don't want to open it just because this is very complicated stuff. I don't want to distract the point, but if you read the title of the paper, it says rate of convergence in bootstrap approximations. So the rate at which your bootstrap way of approximating something that you're trying to measure is pretty good with respect to non-bootstrap sample, which is like without replacement sample. So it's a very simple process, right? You're you're doing something multiple times. You want to just average it to get the final answer. The only trick is you take sample with replacement instead of without replacement, and you'll get a better answer. Is what this is. So that's why this is very popular. Bootstrapping. It can be used when you're trying to estimate anything, basically, not necessarily just proportions.
So in real world examples, so I think this is the way I'm thinking. For example, first time when I ask a question on someone, like they said that, okay, Republican. Second time when I asked them question again, replacing back means during that time they got impacted with other population. And this time they said the demographic. So it looks like whether the answer decision is changing in between two different scenarios. In such kind of examples is good fit, or is there any specific good examples to talk about that? In which scenario random forest? Like I know you said that there are 100,000. We cannot go with 100,000. We can take a sample and based on the sample we are evaluating. But in addition to that, is there any good examples?
Yeah, I can add. I want to add a couple things here. In addition to that, especially with the random forest. If you build one tree, so wait, if your random forest, I said, is a bunch of decision trees, right? Your decision trees are the individual decision makers of what they think about whether an email is spam or no spam. Now, if I decide that I want to take decision of 100 decision trees, I want to build 100 trees from my data, for example, and then I want to combine this, right? Now, what I am saying is, if your data set is 100,000 emails originally, if you build each decision tree on all the 100,000 emails, right? So you build 100 trees, but each tree looks at all 100,000 emails and then average that decision. That is one option. Another option.
So you mean separate, like I'm taking 100,000 emails and you want me to split into 10,000, 10,000, 10,000, then like 10 decision trees, then you want me to aggregate all the 10 decision trees, right?
It is not more about 10, it is still going to be 100 trees. I'm not trying to preserve any computational efficiency or anything. All I'm trying to do is I decide I will take 100 decisions, 100 opinions from 100 decision trees.
Okay.
I have three options. One is 100 decision trees. This is the simplest option. I mean, this is an option we will definitely not go with, which is 100 decision trees, but each tree looks at is built on all the 100,000 records of data. Then you combine that by averaging or weighted average, whatever. Average.
So when you are taking in all 100,000 emails and 100 trees, means every time the different model, like one is in the SVM, one is in non-SVM, some other model, you mean?
It could be some other model, but in random, it could be similar. There is a very applicable concept for everywhere. But to be specific, not to confuse, in random forest, literally, it's always a decision tree model. I will tell you what a decision tree model is. Literally, it looks like a tree like this. But each time, when I say I'm referring to a tree, I'm saying I'm looking at the training data, and then see at each node of the tree, I will take a decision based on some variable of the training data. So So I can say how many times some particular word got repeated in this email. Maybe that word, if it is many times getting repeated, more likely to be some sort of a spam or some scam or whatever, right? Versus how many official words got repeated, which are not in the list of banned words or whatever you think. Then
Okay,
that will be your first decision maker.
got
Then
it.
you will use some other variable. Each time you make a decision, you say you go either left or right, right? So first time maybe based on third variable, here fourth variable, now I'm using, maybe here I'm using seventh variable, different variables could be used. Then I make a decision, and once I come to the leaf, then I have literally spam or no spam written here in each of the leaf. So when a new email comes in, it will go through the same process. It will check whether it will traverse through the tree. And maybe one particular email ended up here and this ended up to be no spam. So then I will see this email is not spam. But another email based on again its data, it will go here. Then it says spam.
Okay, got it.
Now this is one complicated decision maker. In our balls example, the decision maker was ourselves, right? We were literally counting. But here ourselves is replaced by this tree. Now we have different options. We can apply all the 100 trees on each tree. It looks at all 100,000 records. There are two other options. Second option is we take a subsample of maybe 10,000 records, but we do that many times, like you said. But on each subsample we are sampling without replacement. So I'm taking a random sample, but without replacement. And then on each subsample, I fit again this tree. I generate some tree. So I have this as many B subsamples. I have B trees, but these trees were built on each subsample that was without replacement. Then I again average my answers. What do I mean by average? Literally, I'm averaging what each tree thinks about each email in those 10,000 records. So each email goes through the tree, and in the end, the tree for a particular email might end here, whatever. And then there is answer spam or no spam. Again, another tree it will go through. It will do that for B times. But
one question here.
Yeah.
First, let's make it 100 emails. Okay.
Yes.
So S1 and S2. Those 100 emails is already split into 50-50.
Sure.
Based on some scenario, right? Sure. And again, that second level is the SL1, SR21, and again the down. So by this time, this particular child left side already got only some sample. Okay.
Which is good.
So next, when you said that, okay, whatever, when you're repeating, then left to the other child, one of the child will get the different answer. So the average is nothing but always you are going on only based on some subset only, right? Not entire here.
Yeah, all the trees will not be exactly the same, yes. Because some slight modifications will happen between all the 100 trees I'm building, for example. And
okay,
also each tree also, obviously here all records you're looking at, all records in your email. Then once you go here, since you already narrowed down to a smaller subset here, then within that smaller subset, again, based on some particular variable, you're making a decision. Again, smaller, you're going down.
Okay, so your final answer, what you're saying is the bottom thing we have to average. Your model should be bottom.
Yes.
Average it, and based on all these threads, then decide whether spam or not on one thread.
Yes, but but this tree I'm gonna do 100 times.
Yeah, that's what my question. Even if you do 100 times also, again, what is the difference comes? Again, it comes same, right? Do you think that changes?
Yeah, it changes because if I am sampling just because of randomness, because it's just like a dice, right? If I roll a dice 100 times, the standard fair dice, every time I won't get the same sequence of numbers between 1 and 6, right? Some different variation is coming.
Oh, this is a good example. You are right. The first time when you dice, maybe you will get 5. Second round, when again you do the first round, then again maybe you'll get 5. Okay, makes sense. Okay.
Yeah. Now what will happen if your dice is fair dice, like just the standard dice we people use? Then if you do this subsampling many times, and if you count how many times 1, 2, 3 each digit is coming, if you plot a histogram or look at that distribution of counts, it will literally be uniform. If you roll a few times, then it will not be clear. But if you roll your dice 1,000 times or 100 times, and if you count, your 1 to 6, all numbers will be equally likely, almost closer, similar distribution. If you do it 100,000 times, equal times you will get 1, 2, 3, 4, 5, 6. Okay. But your data set, but here, what are we looking at? If you are trying to estimate whether the dice is fair or not, then this experiment is good enough. Okay, but if you had an unfair dice, now I won't tell you, for example, if you had an unfair dice where maybe 3 is more likely by some amount, but there is different amount of proportions, they're not equally likely. And if my question is to you, how do you estimate what is the proportion of 1, 2, 3, 4, 5, 6, right? Because say if you're going for gambling just based on the dice, and if you know this proportion beforehand, you will put all your money on the number with the highest proportion instead of putting on the lower proportion. Then if you try that many times, it will be more likely you will win with respect to other numbers, right? So, but how you want to estimate this, but you don't know the answer. I only told you it is unfair dice. Then how do you estimate it? It's again the same as the red ball, blue ball thing, right? Once what is sample, all the dice, if you throw it and if you note down the number, then it is sampling without replacement. But what you want to truly estimate, you will do better if you sampled it with replacement, right? So without replacement means I throw a dice, one came, I took one out of my dice. Now one will not fall in my dice. Only number from 2 to 6. That is known as sampling without replacement, right? So this is not good enough. I'm saying with replacement is good enough. So naturally in dice it is happening with replacement because you cannot take the number out of your die. So once you take one out, you are putting it back. So you're not disturbing it.
Correct. Basically, with replacing is nothing but you are repeating the same 100,000 emails again and again. This is nothing but with replacing.
Yeah, when you take a subsample, whatever you took, you putting it back again. Again, you take subsample, it may or may not come. So repetition is possible. In sampling with replacement, repetitions are possible. Without replacement, repetition is impossible. Right? Because once I took one out, I will not see one again. So how will I even estimate in the future if I do that many times? After 5 times, obviously I'm done with all my numbers. But if my initial set of dice had 100,000 numbers, or I don't know, maybe 5,000 numbers, but if I'm taking things out, then I cannot estimate the true proportion of each number in the future because I'm disturbing the whole distribution of the behavior of the numbers in the dice. So that's why with replacement is a very good thing. In dice, we are naturally doing it because we are not disturbing the dice. But in the bucket of balls, physically you can remove or put it back. It's up to you. So all the theory is saying, the bagging is, if you take subsample with replacement and compute whatever you want. Now in our particular situation, to be specific, what we are computing is the random forest decision. So what we will do is the follows. Now you understood what one tree is here on the whole, right? We are making decision making. Now let me just draw very clearly and say how random forest is using this with replacement, without replacement, what it is doing. It's here. So let me be very specific now. You have a data set of n records. Let's call 100k emails. And each email you're collecting, I don't know, p variables, right? So maybe 10 variables about each email. Okay, 100k emails in rows. Okay, and we have columns are like 10 variables. This is your in original data set. Nothing has been done yet. Now you have a capability of building a decision tree, and it's up to you if you pass all data set or you pass subset. That's a third point to decide. But second thing you have is with you a capability to build a decision tree. Okay, so what a decision tree does is at the first node it takes the entire data set and then it chooses out of these 10 variables whatever variable it thinks is the most important in classifying email versus no email. So maybe it thought the third variable is very important. So based on third variable, it makes some decision. If third variable is looking like this, then I will think it will have to go to this node. If third variable is looking other way around, is seeming like another kind of a behavior, then it goes to this node. Right? Now again, same thing. Here it might think maybe next important variable, given the third variable has satisfied this condition, maybe the sixth variable is the most important. But if third variable satisfied some other condition, maybe seventh variable is the most important to make the next decision. So like that you build a tree and then in the end you have a set of leaves. The leaf will literally have either spam or no spam in it. You have this capability now. Okay. Now what you're trying to estimate is your final answer. You want to estimate is whether any given email is spam or no spam. That is what we are sticking to. Right. So now so if you want to do bootstrap aggregation, what you have to do is follows. You take your original data set, you take a subsample of say 10K instead of 100K emails, original emails, you take 10K emails. Of course, again, you have all the entries for all the 10 columns, all the 10 variables for those 10K emails. But you take not one subsample, you take B subsamples like this, B. So you will have like this B times. So again, another bucket, so on. Okay, you have B of these buckets or B of bags or what, subsamples. But the only condition I'm saying is this subsample you're taking is with replacement. Okay, bootstrap with replacement is what you're doing here. So you took 10K emails with replacement. So you took first email, put it back in, second, some other email you random, maybe you got 7th email, you put it back. Now you got 9th email, like that it took 10K. You do that B times. Each of these is known as a bag or a subsample or resampled sample, whatever you call it. Instead of you have this capability of building a tree. You could have built it on all data, this data, this data. Right? Now you have B times, so you are going to build B trees. Now how many trees? This will give you one tree, so on, so on, so on. You will have B trees. So you have B trees now. Right? I'm not going to draw the whole tree because so many things could happen. But again, this is say a second tree, for example, something. Then finally you have nodes. Again, you have answers. Finally, leaf nodes, which will again have spam or no spam. This is second tree. This is first tree. Like that, you build B trees. So now you have B decision makers. Each decision maker has some decision of making capability. This right when you pass an email, it can say spam or no spam. Because each email will go through this whole criteria. It will come somewhere and it will say spam or no. Now all you have to do to get final decision is just for any trees prediction or classification that you get on any particular email. Say now you have the prediction situation. Now I give you an email. Now you did training, right? The training is done. Now I give you an email which is not from these records. It's coming from again another separate record. So in future, this is like emails I have till today in my data set, my database. Now I trained it. Now tomorrow another email came. Now at that point I have deployed this system already. All these trees, everything, decisions deployed in my system. Now tomorrow another email come. Now I have to use all this intelligence, right? All this training model I built here, all these trees, all this stuff to finally make my business decision. All I care about is being able to automatically make decisions as emails starts coming in quickly, whether each email should be put in spam or no spam, or like in the proper inbox, right? So now what will happen is each email will come. The email, each of these B trees will look at only that same email. And maybe first tree thinks it'll end up in this node and it will say that email is spam. Second tree also thinks it is spam. Now some trees think it is not spam. Like that you will have B decisions of spam and no spam. Right? Now you just take the majority vote or you combine this by averaging how many spams and how many no spams you got, right? So your average count of spam and no spam proportion or total count you'll have. Now based on that, if majority tree thinks it is spam, more trees think they are spam than not spam, then that particular one email you will classify it as spam. Majority thinks it is not spam, then you will call it not spam. Then the whole life cycle is done for classification, right? You have a model, you are using it on feature data. Now, bootstrapping is a very small part of this whole process. It's easy to implement also. Your different B bags of data set you're taking and you're building B trees. Now each bag, all I'm saying is you take the subsample of 10K emails with replacement instead of having done it without replacement. All that is what I'm saying, right? Just the fact that you're doing with replacement actually gives you a better answer is what the theory and the theorems say. And not only for the email example, but here it could have been some other simpler or even more complicated example, right? This could have been classification or some other problem. But for random forests, it uses this idea of bootstrapping as part of this whole pipeline. Now, obviously, there are other things you want to know about. Bootstrapping is not going to give you a tree, right? Now, the question is, how the heck do we even build one single tree, right? Because if you know how to build one tree properly, then you know how to repeat that process. Only thing that is changing is different data set, slightly difference you are getting because of resampling. But you can repeat it again. But you want to have at least in terms of code, right? One function that knows how to build this tree from any given data set. It could be 100K, 10K, million, whatever. So what is a good way of building a decision tree that can say spam or no spam, or some classification? So that is the next topic. So what we did, overview ensemble methods we saw, then I told you what bagging in general is, which is just computing whatever you want on smaller subsamples, but your subsample has to be taken with replacement, and you average, to get your final decision of what you're trying to compute, you average your subsample answers on the subsample. Now random forest is the overall high level pipeline of algorithm, which is exactly what we drew till now. After this is done, then I will tell you how this tree is literally built. But the pipeline is also important, overall process. From here you can look. So you're taking B data sets. So when you say bootstrap data set, he's trying to say with replacement, which is what we were talking about. So you take B data sets of with replacement, and you call that data set Z star, for example. On each individual bag or individual bootstrap data set, so each of these B data sets, you build a tree. Okay, so you have B goes from 1 to B, you get B data sets. On each data set, you build a particular tree FB. So F1 will be one tree, F2 is tree, F capital B will be B trees, right? And then you, for regression, you just average your result. For classification, you take the majority vote, right? This is what I'm saying. If majority says spam, then it is spam. If majority say no spam, it's not spam. Out of these B trees, this is exactly what we drew. Okay. There's one other additional thing that Brayman, the technique suggests, which is when you learn a tree, you can add even more randomness, which is you have original 10 features in that data set I showed you, right? So instead of using all 10 features for each data set, you can again choose a subsample of M features. So you can use only 7 features each time, for example. There you're adding even more randomness, which is even better. So then the only other modification here is this tree will not work on all 10 variables. It will work on again some random set of 7 variables, if M is equal to 7. This is another set of 7 variables it will work on. So 100,000 record, 10,000 records you're taking of 7, but by 10 variables. But again, another set of sampling across columns now. Here you subsampled across rows. Now across columns you're doing the same thing. You're randomly resampling with replacement. So again, you say in this first set, if I took variables 1, 3, 5, so on like that, 7 variables, then maybe in the second set, for this tree, I could have taken the columns 4, 8, but then again 3 might have repeated, for example. So sometimes out of your 7 variables, some variables might be common because this is sampling with replacement. Any randomization sampling you're doing is always with replacement in this technique. So then you're doing 2 levels of resampling, which is also again saying the same thing. When you're looking at a data set, it's because here you have a 2D data set, right? So when you do replacement, you can resample across the rows. You can also do with columns. So that this technique is exploiting both sides. Here first row sample, then with column also. Now you build these B trees, you take average, majority vote. Okay, so that is the overall pseudocode of the pipeline of random forest. Okay, you average your decision. Now an individual tree looks like this. We talked about that. Now the question is, how is one tree built? If you know that, now you can implement this. You have a capability, you have some function that can build this tree. Right? And then all you have to do is write some for loop that does this sampling and uses the with replacement samples and passes it into this function B times. Then you store your answers in, I don't know, list or array, whatever you like. And then you take a majority vote and you get an answer. Now you can implement everything, right? And that is how, of course, the library is implemented. But now we want to know how an individual tree is built. Then the uncertainty is reduced. You know how to build the stuff, the pipeline. So, okay, individual tree. I will go into the details. So again, just not to confuse. So, say you have some true false decision or spam no spam decision that you want to take. At each node, you want to know which variable you want to make the decision on, the split on. This is known as a split, right? Because you have 10 variables. Maybe the truth is based on 6th variable. If I say if 6th variable is greater than this number, then go to left. If less than some number, go to this one. If it's between some range, this number, like greater than some number, go here. You want to make decision. But I could have made the decision on 5th variable, right? And also what 6th, when I say greater than some number, what do I know, right? Is sixth variable supposed to be greater than 100 to go here, and between 50 and 75 to go here, less than 75 to go here, right? Well, this should not be less than 50 to go here, something like that. Greater than 700 go here. How do you know those threshold cutoffs, where to cut off, right? You want to split based on what amount, greater than what amount or less than what amount. So that is the first thing you want to answer. If you know how to answer that, you answer that, then you get a smaller set of data coming till here. On that, again, you choose again the same thing, you will repeat whatever you did, the same process. But now it might say maybe third variable is the most important. It will decide based on whatever that magical process is. And then based on third variable, again, it will make some split. It will decide based on third variable being like what behavior, the split should be made. Right. So basically say if I want to look at the crime history of some person and I have to decide if he's more likely to commit a future crime or not, right? So if I look at his crime history, I'm looking at say 10 variables. I'm looking at whether he committed traffic crimes. What kind of traffic crime? Is it like DUI or like some accident kind of thing, or is it like some minor ticket because he didn't turn his blinker on while taking a right or something, or is it like more major, like he was speeding and crossed the signal when it was red, he has a lot of records. These are your variables, your 10 variables, right? Then I can also look at his sexual offenses. Is he a sexual offender? I can look at if he did any like major crimes, property crime, burglaries. You could, when you say criminal, you have all kinds of people, right? And again, good people, all kinds of people, right? And then not every person who has some ticket is always a major criminal, but someone who has something major could be really major, right? So you want to estimate through your model in what bucket you would put him in terms of future crime, right? Is he more likely to repeat it, right? So what is a way to build my tree? So if my only two things I want to answer is he's likely to become a major criminal, is not likely to commit another major crime. Only two decisions if I want to make, right? Instead of spam, no spam, I would say major, not major. What will I look at? I will look at his 10 variables, all his crime records, all the property crime, traffic offenses, sexual offenses, everything. And most good people might have 0 everywhere, right? All these things they might not have ever committed in their life. Fair enough, right? Maybe a lot of belief. Some people, of course, might have committed. Now, what is the best variable? Do I want to make my first decision to get a good tree that can classify major or no major? If I want the best classification accuracy in the future, I want to deploy this in, I don't know, in an airport or in FBI, whatever, in the system. How do I deploy it, right? I want a good classifier, obviously, because I don't want to say innocent people are more likely to commit major crimes. I don't want to say a major criminal is more likely to not commit a major crime. Then it's a bad tree. My goal is good classification. So if you want good classification, you have to decide at each node in random forest which is the best variable to first decide against. So one tree, maybe one person can say, maybe first I want to look at his traffic offenses. If your traffic offenses are minor, then maybe everything else may be good. But that may be bad decision, because like even there could be a very major criminal who is a great driver, who is perfect on the road, but he may be a major criminal on some other front. He may be a bank robber. How would you know? He's great at driving, right? He doesn't ever get a ticket, in his last 20 years, for example. So that may be a bad way to decide whether you want to separate your data set into major or non-major criminals. So a good way to, better way to decide is maybe possibly someone may say, maybe I want to look at serious offenses and count how many serious offenses he has ever made. If someone has done one serious offense is one thing, but someone has done like 10 serious offenses, then maybe he's on the FBI top 10 list. Maybe he's like absconding or something, right? So what variable to split against is what you want to decide here. So I gave you different options, right? Traffic variable, or you want to greater than, less than some number, or you want to look at some major offense. Again, within major offense, you want to look at sexual offender first, or with higher preference, or you want to look at the another variable of some property crime or some burglary or some larceny or whatever, some violent behavior or some murder, whatever. So that decision, what variable to pick, is what you first have to choose. Okay, then once you pick a variable, you want to know at what threshold you want to cut it off. So if you picked, say, some major offense here, then you go down, then maybe traffic offense is the last thing you're looking at before deciding good or not. Or it could have been the other way around. But this tree will decide what variable has to be split on first. Then second, what variable here. Then based on what variable here, right? If you go through this path, here you may first choose one variable to split on, and then here another variable to split on. This variable you're splitting here may not be the same if you went in this path. Maybe it got split through this variable, and then here it got split to another variable. It's a different process. of decision making. In the end, you have your final answer: major crime likely, major crime not likely. Based on that, the I don't know, FBI will do whatever, for example. So this is another example of a decision tree, what it is supposed to do. So this is what it is showing here. Uh, Here it is trying to pick out of your subset of all variables, capital I. It is you want to maximize some criteria. We will see what that criteria is. But you want to find which variable out of those I variables, which jth variable has that maximum criteria. Now, what is that maximum criteria that people are using? It is known as entropy and mutual information. I will show you that in next slide now. But basically, all it does is you have a criteria. Now, for each variable in your 10 variables or I variables, you compute that criteria, and for whichever variable the criteria is the maximum, that goes in this node. Now after that variable is out, now in the rest of the variables whichever is highest after given this decision, you go to this node like that. Okay, so at any particular node you want to make decision left or right, and you want to know based on what variable you want to make that decision. Here where you look at what is known as information gain. So this again giving an overall approach here, but again I will tell you why information gain is a good thing to look at. But this is like the big picture again. At any given node, if you want to make a decision, the criteria you will use is information gain. There is different things I'm throwing out here. H is known as entropy. We will define this in the next slide. And basically what it is looking at is, it is looking at the entropy of all of your variables in this first term. And then it is looking at entropy of each individual variable in the second term. And it is comparing how far each individual variable is away from this variable. Now, what is entropy, right? We all heard about probability, which is all about probability is how probable is something. Means you are trying to measure some certainty. If probability is low, then it means it is uncertain, of course. But if probability is high, it means more certain to happen some event. Entropy is the other way around. Entropy is measuring instead of probability. It is a way to measure uncertainty. So if there is a lot of randomness and uncertainty involved, a lot of chaotic behavior, then entropy is very high, which means a lot of uncertainty. So basically, H of S is the total uncertainty you have in your data set, and you, based on which variable you pick, it is trying to see how much well you are able to reduce the uncertainty. That's the difference. So the particular variable out of your I variables that reduces the maximum uncertainty, then it means you have more information gain if you make your first decision based on that variable. So that is the concept of information gain. This is information gain. This is entropies. Right. Now, let me tell you a little more about entropy. Then we can compute this. So basically the end decision is like this. You compute information gain for each of I variables, right? So for each j goes from 1 to however number of variables you have, you compute the information gain. And then whichever gives you the maximum information gain, the theta belong, whichever j will get the maximum information gain, you make your first split based on that. That is what he's showing in these diagrams here, right? So there are different kinds of splits you can make. We have this classification problem. Four classes are there, but two variables you have. Now, if you can make a split here, for example, and say if this particular variable is less than this value, then it falls in left side. If it is greater than, it goes say another direction, right side, for example. Right? You can make a split like this as well. Right? Now, if you see here, some mistakes are happening, right? Blue is falling in here. This class mix is happening, right? So there is a mistake going on like this, but you're also seeing same blue occurring on both sides, red occurring on both sides. They're not being separated, these classes. Here, at least all blue are on one side and all red is on one side. This whatever green, this green, light green is also separate. But still here you're making mistakes. Of course, I get it, right? Which is between blue and green, you're not able to separate. But at least blue and green, you're able to clearly separate from red and this green behavior. Okay? Darker green behavior. Now, at least, but so if you see the information, this is the original data. Information gain here was 0.40 based on this split. If you split based on this variable. Here it's a 2 variable problem, right? Instead of 10 variables. Now, instead if you split on this variable first, then your information gain was 0.69. So then random forest says, first node, I want to split based on this variable. This variable could have been, I don't know, height. This could have been, I don't know, like number of crimes, whatever it is. Right? So this is the concept. Now this thing, it will repeat again and again. Once this has been done, now you go left-hand side, right-hand side based on this, whatever it is, this way split. Then the next question is, Once I split my data, now next decision what variable I have is what decision do I make based on this variable? Do I split here? Do I split here? Do I split here? Now if you see, maybe if I split here like this, then you can see this just these two lines, these splits based on two variables are going to separate blue, green, red, and this dark green into 4 different classes perfectly.
So here, can you explain the left side, the formula, the H of S, so entropy of S equal to P of sigma P of C log P of C.
Yes. So this is exactly what I will actually cover in the next slide. So same.
Okay.
Yeah. So yeah, I'm giving like big picture like this, then we dig deeper little into something, or we're digging deeper some more. So once entropy is known, then you know, basically this split is being made based on this information gain, right? So you want to know how to compute the information gain, what is this formula internally, then everything is known, you know, end to end everything. So we will cover that. Okay, so now just for notation, P of X, entropy of anything, right? If you have some set X, if this X can take say 10 elements and your sigma, you're summing across 10 elements, all each element in that particular set, right? Is what this is notation is saying. And P of X denoting this probability. So it's saying what is the probability of one particular number in this set occurring? What is the probability of the second number occurring? What is the probability of the number? And log is, you know, log it, but this is log base 2. Okay, it's not log based 10. Log base, it's log based. It's a logarithm of that probability. So if you compute probability of each number and the logarithm of that probability base 2 and multiply that, you get some number. If you add that up for every number in this set, that is a definition of entropy. Now, obviously, you need some intuition or understand like more clarity on why this is a good quantity and why it is doing what it is doing and all that. But anyway, this is a definition. So as I definitely want to add that understanding as well. So we will do that. We should probably cover this in again next class, but this is a very important technique. Random forest is used very popularly. One thing I wanted to show is, before we close today, is AWS released something called SageMaker, another service. I mean, there are so many services, but SageMaker is a popular service now. It is very recent. So if you are thinking about at scale, right, because this is the world of big data, you want to build random forest or some other technique, right? Neural networks at on a very large scale data sets. This is one of great options. It's very easy to use. It's more like you click a bunch of buttons, and if you know how to evaluate the result and plot, you're good enough. You don't have to, you know, literally code anything. You literally choose and do it. So things are getting very automated. So now,
so Pranit, we don't need to write any code in this SageMaker?
In SageMaker, all your code is like more, not algorithmic code. Your code is like more just to use the system kind of code.
Okay.
Very simple. Like things like what it does is you take an S3 bucket, which is like an instance on AWS, right? One kind of instance.
Yeah.
In that you put your data set, your large data set in that S3 bucket.
Okay.
You have a hyperlink to reach to that S3 bucket. You will tell SageMaker, hey, my data set for this problem I want to solve is in this particular hyperlink, in this S3. Now, now you can say, I want to use all of it as training or 70-30, whatever. You'll take that training testing, you'll tell it, and you'll say, okay, it will give you a bunch of 10 techniques, for example. You'll say, I want to build this particular technique on that. Then it will build that technique, for example.
So basically, it will run like H2O, multiple techniques, and it will give the output of accuracy of the each model. Am I right?
Yes, you can choose what techniques you want to run and not run initially. Then you'll get for accuracies for all that. Yeah.
Okay.
Yeah, it scales up very well. I wanted to. I think I'm logged out of my Office VPN. Next time I will show you the list of techniques. I have to go into it, but it is something I can share. It's not like not shareable material.
Yeah.
Yeah. Sorry? Yeah. I think something chopped out, but yeah. Cool. Anything else, or I think we're good for now? Otherwise?
Good.
Okay. Yeah, great. So yeah, let's continue on to the other second half of Random Forest next week. I think we're at the right pace. I would really suggest that some of you guys have to work on some of these techniques and put it to the resume. So apply whatever, right? I saw Chun was trying to do something on the TensorFlow, but it'd be great if you can apply some of these techniques on some data set, smaller data set, say from UCI repository or whatever online, some classification problem. Do random forest, whatever, neural network or SVM, or do all three. It will add something to your resume, because just stating that you have taken a course is not good enough. There is so much courses on offer and so many things outside. So for job purposes, it would be great to convert it into, and also for your learning, at least the pipeline, right? You may not be end-to-end like some high-end mathematician who understands every single thing, but at least you will be an engineer who is great at building systems and running these techniques, building pipelines, doing business jobs. So you might want to get that amount of level of knowledge, and additional scientific knowledge you will obviously keep getting as you go through your path in the future, if you're interested in that. So yeah, try to convert these into your projects. I think that is even more important than listening to the course. The training and listening course is one part, but doing an assignment for your resume is another part, which is very important. Okay, so have a good one, good weekend. Catch up again. Yep, bye-bye.